All right, welcome to the very last long-awaited section, 12.1. It is inference for linear regression, so you're going to have to think back to chapter 3. So take a moment to pause and just kind of think about linear regression and y hat and what everything stands for. Okay, so what we have here is a scatter plot, and this is kind of going back to that example about eruptions of the Old Faithful geyser. Here there are 222 records for a single month, and they're going to call this a population regression line because it's the population for that entire month. Now, notice that the slope of that regression line is 10.36. Now, if we took random samples, each random sample would produce a slightly different regression line. So notice you have slopes of 10.2, 7.7, and 9.5, all of which are different from the actual slope for the population. So take a moment there if you need to. Okay. So confidence intervals and significance tests about the slope of the population regression line are based upon the sampling distribution of B. So B is your slope, and we can do significance tests and construct confidence intervals just like we did in previous chapters. So just like before with sampling distributions, we are interested in the shape, the center, and the spread. So here we are looking at the sampling distribution of a slope. Now we're really only going to focus on slope. We are not going to look at the sampling distributions of the y-intercepts. Really we only care about the rate of change. So let's talk about the shape, the center, and the spread. Notice shape, approximately normal once again. So the sampling distribution of B will be approximately normal if the values of the response variable y follow a normal distribution for each value of the explanatory variable x. The center then is the mean. So the mean of the sampling distribution of B is beta. Okay, so it's just slightly different symbols here, but not a big deal. What I do want you to know, though, is that this beta is not related to the type 2 error that we did also call beta. Okay, so let's look at a sampling distribution here. Again, this is for the slope. It's a sampling distribution of the slope. So take a moment and just read about the shape, the center, and the spread. Okay, so take a moment to look at this graphic. And notice it says the mean value of the response variable mu of y falls on the population or true regression line. Okay, so if this is your true regression line, what it's saying is that your means of these sampling distributions essentially for each value of x fall on this regression line, on the true regression line. And it says the values of the response variable y follow a normal distribution with common standard deviation sigma. Okay, so take a moment. I think you can do these next couple parts here. So pause and try them, and then I'll put the answers up. Okay, so notice it does say let's focus on the eruptions that lasted 2 minutes long. So we're going to call this kind of a subpopulation, if you will. So we're only looking at those specific eruptions. So what's the average amount of time until the next eruption? We're simply going to plug in 2 for 2 minutes. That's the duration, and we get 54.8 minutes. That's 54.8 minutes until the next eruption. Okay, so we've got a mean, we've got a standard deviation. They gave us sigma 6. So let's talk about this 95% confidence interval. Let's just go ahead and be very approximate with this. Think about the empirical rule, the 68, 95, 99.7 rule. If we want to be 95% confident that all we really need is 2 standard deviations above and below. We know our standard deviation is 6. So if we have a mean and our standard deviation, we can construct an approximate confidence interval here by taking the 54.8 plus or minus 2 times 6. That gives us the interval of 42.8 to 66.8 minutes. So we can make this answer a little bit better by saying we are 95% confident that the next eruption will occur in 42.8 to 66.8 minutes. Okay, so part of our state plan do conclude for any time we are constructing confidence intervals or performing tests, one of the big things we have to do is check conditions. So conditions for regression inference are as follows. There are actually 5 things that we have to check, so please take a moment, pause, and read. Okay, we kind of have an acronym here of linear, L for linear, I for independent, N for normal, E for equal standard deviations, and then there's not really anything for the A, but the R is random. Okay, so this just gives you basically some tools for how you would check each of these things. So again, just pause and read. Okay, so go ahead and read this example, and then we are going to check the conditions. All right, so the first thing we need to check is linear. If you look at the scatter plot of the data, okay, now it looks a little bit different than what we're used to just because we only had data at 150, at 200, at 250, those intervals. But anyway, we see that the scatter plot kind of shows a linear form here, so we should be pretty good. The residual plot also shows a random scatter about the horizontal line, so it's not like it's up and then down and then up and then down or anything like that. It's not a big U. We have data above and below that horizontal line at 0. Independent. This condition is met because the helicopters were released in a random order and no helicopter was used twice. So knowing the result of one observation should not help us predict the value of another. Normal. So the histogram of the residuals is single-peaked and somewhat bell-shaped, so it looks like it could be approximately normal here. What we're usually going to check is the normal probability plot, and as long as this is approximately linear here, we should be good to go. Okay, so going back to that residual plot, we want to look and see if the distances of our data on the above the line 0 and below the line 0 are approximately the same. And you can see that these aren't exactly the same. Like from here to here and here to here is not exactly the same. Even from here to here and here to here is not exactly the same. But they are approximately equal. And then random. The helicopters were randomly assigned to 5 possible drop heights. So the random condition is met. So there might be a little bit of concern about the equal standard deviation condition, but we should be safe performing inference about the regression model in this setting. Okay, so when the conditions are met, we can do inference about the regression model, but we have to estimate some parameters. So the slope and the y-intercept of our sample data, those are unbiased estimators, so they are going to estimate beta for the slope of the population and alpha, the y-intercept of the population. So then we need to look at the standard deviation. If we wanted to estimate our standard deviation with S, what we're really looking at is how far our data is from the line, so we're going to use that residual. Notice in the denominator we do have the n minus 2. Okay, so they have a bunch of formulas here, if you will, and I really don't think they're going to ask you to calculate the standard error. What I would think that they might ask you to calculate as a test statistic. Now notice if you know the population standard deviation sigma, you can use a test statistic z, but that is very uncommon. And so we typically are going to use a test statistic t. We're going to estimate that population standard deviation with the standard error. That's the standard deviation that or the standard error, if you will, that you just looked at on the last slide. So notice that when we find the standard error, it is with a degree of freedom of 2. That's why we divided by n minus 2. Okay, so take a moment to look at that data. Let's calculate the test statistic by hand. Again, we're going to use t, okay? So we're going to take the slope of this line, so 0.005724, so that is your drop height there in the centimeters. It's not your constant. You remember you're looking for the slope here. Minus, we're going to use 0 for our beta here, because that's kind of saying that there's not a positive or a negative association. Divided by the standard error, so the standard error for our slope is right here, that 0.0002018, giving us a value for t of 28.36. Okay, so constructing confidence interval is the same. We kind of talked about that already. Notice that your critical value is t star. Again, just to reiterate, you would be using a degree of freedom of 2. Okay, so if you read this example here and you put your data in L1, L2, you can produce the scatter plot, the residual plot, and the probability plot. So if you look here in your stat plot, I have my data in L1, L2. This would give us a stat plot. Would give us a scatter plot. I have set up over here in plot number 2 a residual plot. So notice I have my list 1 in X and then my residuals in Y. And then if I want that probability plot, I'm going to go over to 3 here that I already have it set up. You want to turn this guy on all the way over here to the right. You're going to keep this L1 and then you're going to turn your data axis to X. Okay, remember when you want to graph any of these, you are going to press zoom 9. So I do strongly encourage you to put the data in your calculator in list 1 and list 2 and see if you can get each of these graphs here. Okay, pause for a moment and try to do A, B, and C. This is good review of chapter 3. Now for part D, I am going to start a new video just because I don't want to run out of recording time.